This is lecture 8 in the series of learning about induction motors, and this lecture is about the torque slip characteristic of an induction motor, and this is one of the most important characteristics of any induction motor. And the torque equation of an induction motor, which was previously derived, can be written as 3 divided by 2 pi ns, and 2 pi ns is also ws, that is equal to directly proportional to the speed of the machine, synchronous speed. And the torque equation can be written as shown here. It is directly proportional to the stator voltage and the stator resistance. Also, it can be divided by the rotor resistance and the rotor reactance square. So this is how the induction motor torque equation can be written as. So what you see is that when the slip is 0, the torque will be 0 from the equation, as it is directly proportional to slip, and at normal operating speed slip will be small and reactance can be neglected. Hence torque will be directly proportional to slip. When the slip will be high, the torque will be almost inversely proportional to slip, and hence a hyperbola graph in this region can be obtained. So when the slip will be 0, torque will be less, and at normal operating speed slip will be small, so the slip will be in the range of 0.2 to 0.4, and in this region the torque will be directly proportional to the resistance. So you can see the torque and the slip characteristics of an induction motor. There are 3 modes or region in this graph. The one where the slip is greater than 1 comes in the braking region, and when the slip is between 0 to 1, it comes in the motoring mode, or when the induction motor is running as a motor. When the slip goes greater than or less than 0, that is when the induction motor is being rotated by an external prime mover and the speed of the machine goes more than the synchronous speed. And at that time the induction motor will output power through the stator. It will feed the power rather than taking in the active power, and at that point it will be known as a generator. And the maximum slip, torque pertaining to the maximum slip, is known as the breakdown torque, and beyond this maximum slip, if the induction motor is taken, then the motor will mechanically fall apart. And during the full load or the normal operation, the slip is close to 2 to 8%, as you can see from the graph. In the normal motor operation, the rotor revolves in the direction of rotation of the magnetic field produced by the stator currents, that is in the synchronous speed direction. This speed is between 0 and synchronous speed, and the corresponding slip is between 1 and 0. This is labeled as motoring region, as you saw in the previous graph. So when the slip is between 0 and 1, that is the speed of the rotor rotation is less than or always less than the synchronous speed, at that time the induction motor will output mechanical power at its shaft, and it will act as a motor. To obtain operation in the region greater than 1, corresponding to a negative motoring speed, the motor must be driven backwards or in the opposite direction against the direction of rotation of its magnetic field by a source of mechanical power capable of countering the electromechanical torque. The chief usefulness of this region is braking the motor to quickly stop the motor, called plugging. So when the motor is rotated in the opposite direction, the slip will become negative, and so the induction machine will operate as a generator when the standard terminals are connected to 3-phase supply, as in case of a motor operation, and the same motor, if it is driven above the synchronous speed by an external source such as a prime mover, if the rotor is rotated above the synchronous speed, then it will result in negative slip, as slip is the synchronous speed minus the speed of motor, which is now above the synchronous speed, divided by the synchronous speed. So that equation, or the slip, will be less than 1 in this case, as the motor speed has risen above the synchronous speed. And when the slip will be less than 1, it will result in the generating operation of the induction machine. And in this case, the induction machine will be feeding back power to the transmission system or the power system. And this kind of induction generator is useful where the prime mover is asynchronous or of varying speed, like a windmill or a water turbine with non-continuous flow of water. In such case, it can be useful to develop power and supply it back to the grid. That's all. If you like this video, please do like, subscribe and comment.